Okay, so this question is about we have a DC machine similar that was given to us in example 4.2, but it has a series winding. So we have a DC shunt generator which has now a series winding. So it becomes a cumulatively compounded DC generator. So, what is a cumulatively compounded DC generator? And it is actually a short shunt connection compounded generator. Short shunt connection means that this is, for example, the armature of the machine, or we can say that this is our armature of the machine. Short shunt means that the shunt is at a shorter distance, then we have the series winding, and then we have the terminal. So here the current IT is flowing, the voltage is VT, this is our series, this is our field, this is our armature. Now the current IA is flowing, this is IF, and this is IT. So the critical equations for short shunt compounded generator we can see is, if you can see here, I of A is actually equals to IF plus IT. Okay, this is one of the equations. Then we can also see that one of the equation, if we apply a loop at the outer lobe, that Vf, the voltage across the field winding, is actually equals to V series winding voltage plus V terminal voltage. And the other equation about the greater loop, including EA and VT, if we apply the KVL, EA equals to IA RA plus IT R series plus VT. So these are actually the critical equations for a short shunt compound DC generator. Now let's see what are we having and what is being required. He has given us the series winding resistance, and what he has also given us is the machine is the voltage is required 100 volts at no load as well as at full load. So the series winding effect should make sure that 100 volts also exist at the full load. And it has assumed, and what it is asking is how many series turns per pole are required to obtain zero voltage regulation. That means 100 volts will also be produced at the full load. So what we have now is, now for the this question we know that VT no load is 100 volts. We require 100 volts, and we have seen that in the equation also to when we were solving this example also, the previous example, the 100 volts, for 100 volts to achieve the 100 volts, this was the curve to achieve the 100 volts. Let's clean all the previous things. And so for the 100 volts we see that a slope of RF equals to 100 ohms will provide us 100 volts. This was previously said. So the RF at 100 ohms will provide us 100 volts for our when the field winding at no load conditions. Now secondly, the point comes that now it is at full load. What happens at full load? We know that this is a 12 kilowatt generator, and so the current armature will be the total current, the armature current that will be flowing through this generator at these conditions will be 12 kilowatt. This is, and at 100, so this will actually give us 120 amperes. So the generator will be producing a current I armature that will be equals to field current plus the terminal current that is equals to 120 amperes equals to IF plus IT. This is equation number 1. Now let's look at another important thing when we have seen the equation that V of F is equals to V series plus V terminal. V of F equals to this plus the V terminal. Now V of F is IF RF equals to V series is actually IT into R series plus V terminal. Now at the full load we need 100 volts and the terminal current we don't know, but the series resistance we know it is 0.01 ohms. Here it is given, and the value of RF that we also know at no load it was for 100 ohms we were getting 100 volts. So this is also 100 ohms. So the value of IF will be IT 0.01 ohms plus 100 volts divided by 100 ohms. Now we consider this to be equation 2. Now here we have two unknowns, here we have two unknowns. If we solve these two equations simply, we will get the value of IF equals to 1.01 amperes and the value of IT will then become, by this equation just putting it, it will be 118.99 amperes. So these are the two values that we get from here. So at full load, when the voltage we have at the full load, when we will be requiring this, how much should be the internally generated voltage so that at the output we get the terminal voltage. We can calculate it like this. So what it is saying is we want to know EA and we know that it is IA RA. For here we have written down the equation for a short shunt connection, plus we have IT series plus V terminal. We want 100 volts. Our machine is fully loaded. The terminal current we have calculated is 118.99 into R series. What is the series resistance? 0.01 ohms. And for IARA, what will be the current of the armature? That is 120 into 0.1, that is a series resistance. So the value of EA that we will get is 113.2 volts. So this is the value when the machine is fully loaded. Its internal voltage should also increase to this value due to the series winding and its effect of increasing the flux, so that the output voltage will remain same, not changed. So how can this EMF be generated? Let's go to this magnetization curve. Let's go to this magnetization curve and let's look at, if we clean all the other things, what it is saying is we want to generate 113 something here the voltage, and something here will be the voltage where that will be actually be produced by a current that will be around here somewhere. This will be the voltage that will actually produce. So this should be the internally generated voltage 113, and this will only be produced when the effective field current inside the machine, the effective field current means the current that is producing the flux in the machine is equals to 1.45 amperes. Now if this will be what is being required. Now if I can inform you that and revise you that the flux in the machine is now being produced, the total flux in the machine is now being produced. So what can I say? The effective magnetomotive force that is being produced inside the machine is actually due to the field winding, it is this one, and due to the series winding, it is this one. And effective field is actually equals to the number of turns that the field winding has. So if we look at this, because it is taken from the magnetization curve produced by the shunt windings, so this will be equals to NFIF plus N series into what is the current through the series winding? It is the I terminal. So we can see that it can be also be written as I field effective equals to IF if we take this to the other side plus N series over NF to I terminal. Now we know the value of I terminal, that is 118.99. We know the value of field winding, it is 1200 turns per pole. And we know the value of IF that we have calculated here. That will be the current flowing 1.01 amperes. We know the effective field current 1.45 amperes. So we can calculate the number of series turns that will be equals to approximately 5.04 per pole. So this will be the number of series winding turns if they are present in the machine. It will not allow the voltage to fall down. It will not allow the voltage to fall down, but it will be a flat compounded generator at full load condition. It will be 100 volts, and no load also it will be 100 volts. Thank you. I hope it helps.